Okay, right. So we are starting. Now I know there are some questions, so I'm going to start with yours. But before that, for the benefit of everybody watching, new stuff on Canvas for scene announcement I made. Lecture notes of me, by me, on general equilibrium. A bigger lecture note set by Jonathan Levin for those of you who would like to read more details. That's not required reading. Mine, I would think, is. Because it's kind of an introduction also to reading productively variance chapters and practice problems for general equilibrium, which I would like you to attempt at least before November 28th. All right, so you will get these 2 weeks. This is a substitute for the class that we would have after the exam, which we will not have. All right, so that's the announcement I want to have out there. Now your questions. You asked about the Le Chatelier principle.
Yes.
And as it connects to the envelope theorem and then therefore to the duality results we've seen that come from the envelope theorem, right?
Yes.
Okay.
Yes.
So I'm going to give you a geometric interpretation because the math you've seen.
Mm-hmm.
So hopefully that will give, and hopefully that's an interesting question for all people present. So I'm going to consider a very simple maximization problem with one variable. So by choice of x, I'm going to maximize this thing. And I'm going to assume that there is a constraint. Now, this method will only allow me to have a constraint that is a weak inequality. Otherwise, if I have only one variable and one constraint that's equality, then I am only allowed one feasible point and the whole thing becomes trivial. What's the best way to do it then? Okay, so suppose that we do it this way. I have two variables to do the maximization. And I have a constraint. No. I have a constraint that goes something like gxy equals b. All right? So I'm going to consider b my parameter. And of course, x and y are going to be found optimally as functions of b. So we solve it. Suppose we have a unique solution, second order sufficient conditions satisfied, it's a global maximum, etc., etc. Okay? So then we get our x star of b, and we get our y star of b, right? And then our maximized function, which I will call by v, because it's a very common thing in math, and also as you'll see in macro, the value function it's called, right? The maximized function. So v of b is defined as f of x star of b, y star of b. So that's a very generic kind of problem that if you add enough variables and constraints, it then can encompass all the examples we've seen, right? So you can then consider this value function, right? And consider also maximizing this in the absence of the constraint. All right? So the example that I always keep in mind to motivate this is short-term versus long-term, short-run versus long-run inputs, right? So this could be a short-run constraint, which could be present or it could be absent, right? So suppose you could also do your problem without the constraint. No constraint whatsoever. And suppose this also has a well-defined solution. Okay? but I will introduce the parameter b here as well, all right, which is not the choice variable. So now, suppose I make a graph of the value function with and without the constraint. So let's put a little g here for the first value function to remember that's the one that comes when we do have the constraint. And over here, the corresponding value function shall be written simply as v of b. Right? Obviously, even though there is no constraint, since the parameter b is lurking in the very definition of the function f, and it will affect the first order conditions, and therefore the optimal values of x and y will be depending on b. I needed to have it there because how am I going to graph the value function without the b here? So suppose then I want to graph here the value functions, right? And suppose that the value function of this one without the constraint is, let's make it the simplest way possible. It's constant. It doesn't care about b. So in other words, I formally introduced b. You can always introduce into a function another parameter or variable with a zero coefficient in front of it, right? So then v of b is this. I'm simplifying as tremendously as I can because there's one particular point I want to make. And it doesn't pay, I think, to make this comparison problem without the constraint any more complicated than it needs to be. Now, suppose there's a particular value b star, that's the original, some starting point value. All right? Now think of it this way. You would be at this point in the absence of the constraint, and you would be getting this value, this maximized value, right? If your problem with the constraint happens to give you the luxury of having the exact amount you would like optimally, then your constraint does not bother you. Your two value functions are achieving the same level, same height, right? So, but if the b you actually have to deal with is not that, right? Then your constraint is actually impeding you from achieving the overall maximum that you would have been able to achieve the absence of the constraint. So both to the left and to the right of b star, your value function vg with the presence of the constraint has to be below, right, the unconstrained level of the value function. There. Now you see the tangency, right? Now the book, of course, doesn't force it to be horizontal, and it says, okay, it can be the tangent to like the profit function, for example, or the cost function the other way. But at the point where you accidentally have the exact amount of the constraint that doesn't bother you, the two are tangent. From that, you build the envelope theorem and so on. But that's, I think, the intuition that will help you. Is that the kind of answer you were hoping for?
I think so.
Okay.
Yeah. Yeah, that makes sense.
Okay. Everybody okay with that?
And so, like in relation to when he does in Varian, when he does the short run, long run stuff, the v without the constraint. In this case, the VB is just is considered the long run, and then the VG, yes. if it was in here, VG would be your short run with whatever that constraint
Correct.
is on. Okay.
That's right. Yes.
Okay.
And it is, even if you have a constraint to use a specific amount of capital in the short run, right? Mm. It may accidentally, it would be very unlikely, but it is very possible that you have exactly the amount of capital that in the long run you would have liked to have had.
Okay.
Right?
Right. Okay.
Then you have this coincidence of the two values of the value functions. And any other point, the constraint actually bothers you and lowers the value you can achieve in the presence of the constraint.
Okay.
Okay?
Okay. That makes sense.
Okay, so that was one question. So that covers essentially your first two-parter question, right?
I believe the envelope theorem was more of the. It goes into a little explanation about like how we the derivative properties of profit and cost can give us the supply function and the factor demand.
Yeah.
And I was just a little. It says like, oh, this is an application of the, or like this is because of the envelope theorem, and I was just a little. I wasn't doing a good job of seeing it.
Okay. Yes. Okay. Remember that few pages I scanned and put up on Canvas for Mascolel, Winston, and Green, where we have the minimum function of a convex set and so on.
Yes, was that the duality?
Yes, that's
Yes.
from the duality. Essentially, those duality results are kind of a cousin of the envelope theorem.
Okay.
So, if you're okay with the meaning of using this stuff, for example, you have a profit function, you take a derivative, and you know what you're getting out of it. If you know that, then that's okay, since I'm not going to require being able to prove how these are related and so on. So then I wouldn't worry about that.
Okay.
Unless it's impeding your understanding of what are we really getting when we take a derivative of a profit function, for example.
Okay.
But you get the supply function or the input demand.
Right.
Careful with the signs there.
Right.
Okay, but apart from that.
Okay.
Right? Okay, so just take it for, take it as a little shorthand because he also doesn't want to give you the full proof. The Handbook of Mathematical Economics, second volume, I believe, all the way back in the 80s that volume came out, has an entire chapter on duality. Okay. So anybody who gets fascinated, and I welcome that, I'll just tell you what it is.
Cool.
And then you can see the whole proofs and all that stuff.
Okay.
We got a bit of an idea of the proofs already.
Yeah.
Okay, so that's that. Then you had the Kuntaker.
Yes.
So I'm starting with you since you have all those questions. Thank you for starting that discussion, and then I'll open it up to the other two illustrious people present. So you said the problem in the example, pages 14, 15 in the Wainwright's chapter, right?
Mm-hmm.
Here, this thing. Lecture notes.
Yeah.
This thing. All right, so tell me what it is that is confusing.
I think it's just general. Like I understand the theory behind it. I understand the we use Kuhn-Tucker when there's the chance that our function might not, our maximum might not be. It might be at a boundary point instead of being an interior solution. But I guess I have a disconnect between how I should know when to use it or how I should implement it.
Okay, all right.
So
here's how you know when to use it. If whoever gave you the problem is worth his or her salt, they would have given you the definitions of the domains of every single function involved. Okay. And I've seen plenty of problems from universities I shall not name that leave it implicit. And you're supposed to understand when you're supposed to say the domain is, R2 plus. Mm-hmm. So, all right, in any case, you would know to use it if either explicitly the problem states the choice variables must be non-negative, or have some other constraint of that sort. It could be that, for example, if one factor of production is labor time, and you put it in a negative because you're writing it as a production set, right? Then a reasonable constraint during a single day of productive work, is that factor of production is greater than or equal to minus 24. Okay. Right. 24 hours in a day, right? So any problem like that immediately should make you suspect, boundary possibility, right? But that is actually even more general. the Coontacker approach is useful for any constraint, right? Any constraint that is weak inequality.
Okay.
Because what's the story there? If you have a weak inequality constraint, it may bind or it may not bind.
Okay.
In
Right.
all of those cases, you get a complementary slackness condition. You get three things, right? So let me write the constraint. Suppose you have a constraint that is g of sum x's, this is a vector x, less than or equal sum b. Okay? And you want to take the partial, you will have a associated Lagrange multiplier, right? And then you say, okay, now for this constraint, I'm not going to do the partials with respect to x of the Lagrange function. I'm going to just do the constraint, the complementary slackness triplet of conditions that goes with this particular constraint. Okay? So, one thing is, so first order conditions just for this constraint. Three things. First, the g of x, of course, must respect the constraint. By the way, in order for this, if it's a max problem, in order for the next thing I'm going to write to be correct, you need to write the constraint like this for a max problem in your Lagrangian. In other words, your lambda should be multiplying a non-negative thing.
Okay.
If you want to write it as minus lambda of g of x minus b, I don't care, it's of course the same thing. So you see it one way or the other in books and it's the same thing, right? So for me, for some reason, I like to have the plus in front. And then my mnemonic is my Lagrange multiplier has to be multiplying the constraint in a way, written in a way that what's in the parentheses is non-negative. If it's not given to you like that, the constraint, then flip it around and make sure that what you enter here is the non-negative version of the constraint. Okay? All right. Having said all that, then the multiplier corresponding to that constraint must be non-negative. And finally, the complementary slackness. Let's just keep it, doesn't matter for this, but I'll keep writing the constraint in the non-negative direction, so to speak. Okay? So again, the interpretation, and all of these, I should say, are supposed to be for, some optimal solution. So, star. Yeah. Okay, so, interpretation. Number one, the most obvious, you respect the constraint. Number two, if you wrote your Lagrangian right, your multiplier will be non-negative. Interpretation. It's either going to be 0, which means the constraint doesn't bother you at that moment, or it's going to be positive, which means that the constraint bothers you. And you could have achieved a higher value of your objective function if the constraint were not there, or if it were relaxed a little bit. If somebody gave you a little bit more b. All right? Okay, so this is a general thing we will apply. I don't care, in other words, what the form of this, the exact form of that is, right? What if it looked like this? That's the same as saying xi is greater than or equal to 0.
Yeah.
Ah! Now remember the little note, 2-pager I gave you, where I introduced in the Lagrangian constraints like that with their own dedicated multipliers.
Right.
That reduces to the Coontacker conditions for the non-negativity constraints.
Okay.
It treats it, in my opinion, symmetrically with all the other constraints. So it's more pleasant. So in that case, you wouldn't have the inequalities, the partials with respect to the xi less than or equal to 0 for a max problem, or greater than or equal to 0 for a min problem, right? You wouldn't have those. You would have everything equal, but there would be a plus, let's say, mu,
Right. Okay.
which when you move to the right-hand side, it will be minus mu, which is then automatically not positive, because if you write it carefully here, the multiplier will be not negative.
Okay.
Okay?
Okay.
So if you understood this, then think of the non-negativity constraint, something like that, arm it with its own multiplier,
Okay.
and then your complementary slackness conditions come from like any other.
Okay.
And they mean the same thing. So in particular, if the multiplier is positive, that means you've hit the constraint, at this point some axis because you hit the boundary, and you can't go any further, but you would have liked to have gone further, and this tells you that that's the case if it's positive. On the other hand, if you haven't hit the constraint optimally, then it means you stopped before and it doesn't bother you, and then the lambda will be 0.
Okay.
And that is, of course,
Right, and that's where
the meaning of the complementary slackness, the third of
Okay.
these. So I don't know. For me, it is the best way to keep everything symmetric by introducing everything as an explicit constraint. Others think it's more elegant or practical to not introduce it and write the inequalities in the first order conditions. Your choice.
Okay.
Does that answer your question?
I think so.
Okay.
Yeah, I think it's going to be something obviously I have to practice it and play with it.
Right. I mean, introduce variables in this problem. Introduce additional Lagrange multipliers.
Okay.
Right? And work it out and see how you get the exact same conditions as he does.
Okay.
Okay?
Thank you.
Sure. And if you have Simon and Bloom, they do discuss it.
Okay.
That
Yeah.
you don't have it, now you know how to do it.
Yeah.
Other questions? Okay. Brianna?
I had questions from the midterm to practice.
Sure. Okay. Well, let's see how much I'll
Okay.
allow myself
I
to
know.
answer, but I'll try.
Well, I only have one question right now.
Yeah.
I guess it was just for problem 1. I am a little confused how to, or problem 2, I'm sorry, to incorporate the identity that you give from problem 1.
Okay. How did you start it?
You mean problem 2?
Yes.
Just the partial derivatives,
Of?
the profit function.
Right.
Oh.
And these gave you what?
So then you get the supply function and the demand, factor demand.
Factor. Is that the constraint or the unconstrained factor demand?
The unconstrained.
Correct.
Yeah.
Okay. Now, what is your objective? What are you trying to find?
The cost function.
Yes. The cost function will be equal to the sum of the wi's multiplied by the constraint
Right.
functions.
Okay.
You have found the unconstrained functions.
Right.
Hmm.
Okay. I see. Okay.
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 Okay. Now you have a supply function which
Yeah.
will allow you to connect the price P with the output.
Okay.
Got it?
Okay.
All right.
I see.
But if you try to use that, then at some point you have to transition to using the the constraint xi's.
Yeah.
Right?
Right.
It's not something that you will need to do work. It's just I want you to recognize
I see.
that you're shifting a function with one domain, the unconstrained, to one with a different domain, the constrained one,
Okay.
right?
Yeah.
And then in order for you to claim that that is valid, you need to make reference to that identity.
I see. Okay.
Okay?
Okay. Okay. that
I
makes
had this question earlier with someone else who
Okay.
was asking me.
sense. Okay.
So I'm glad you asked it, so now everybody hears how it goes.
Okay.
Was that clear
Yes.
for everybody? Okay, good. Anything else from maybe the practice problems? You're done, Brianna?
Yeah.
Good? Olena?
Yeah, I just still haven't had time to look at it.
Okay, got it. Luke, practice problems?
I'm still like working through them. So
Okay.
yeah.
All right, so then I'm going to stop this because, it becomes a huge file.